Hello everyone, this is a run through the electric circuits questions, exam questions, which are part of the A-Level Physics Year 1 workbook. The suggestion is that you get a copy of the workbook and print it off and have a go at the questions under timed exam conditions. You can then use this run through to help you with any questions that you found tricky and to help you to get a bit more of an insight into what was needed for those questions, so you can understand them better, and you can then, if similar questions come up, you can improve your grades in physics. So we're going to scroll down. You may have already had a go at the mechanics questions. There is a separate video on those, and so we're going to start with electric circuits. Question 1a, state what is meant by superconducting material. So a material with zero resistance, or just no resistance, at or below the critical temperature. So 1 mark for each point. B, state an application of a superconductor and explain why it is useful in this application. So an MRI scanner, because it has a strong magnetic field. Maglev train, particle accelerator could be examples. No energy dissipation or no heating effect. Microchip or computer can be smaller, faster processing speeds, and again you could say no heating effect or no energy dissipation. There's only one application that's needed and one explanation of why it is useful. 2, it's a current voltage graph, which we call an IV characteristic for a filament lamp. So you need to sketch that on. So there's 1 mark for a graph which curves over like this, curves in both quadrants, and the second mark is for the graph being linear through the origin. So straight line for this bit as it passes through the origin. This region can be very small, but it does need to be there. B, part 1. State what happens to the resistance of the filament lamp. As the current increases, the resistance increases. Part 2, the filament lamp is non-ohmic, and that's because resistance is not constant, or we could say current is not proportional to potential difference. So for 1 mark there, we need to include the explanation as well as saying non-ohmic. C is the circuit with 3 lamps which are identical, P, Q and R, connected as shown. If the lamp Q melts so that it no longer conducts, explain why lamp P becomes brighter and lamp R becomes dimmer. So P on its own has a higher resistance than P and Q in parallel has. So the potential difference across P will increase and it will reduce across R. And that would get you 2 marks. Or alternatively, you could say if Q blows, the overall circuit resistance increases. This makes the current through the resistor reduce. So R is dimmer. Current through R it reduces, so R is dimmer. Or the current, although lower in total, is no longer splitting at PQ, so the actual current through P increases, so P gets brighter. So that would get you either of those, the sort of 3 options there really, to get the 2 marks. For D, we're given the power rating of filament lamp X. It's rated at 60 watts, 230 volts. Another type of lamp, Y, is energy saving, is rated at 11 watts and 230 volts. Calculate the electrical energy converted by each lamp if both are on for 4 hours a day for a period of 30 days. So X, it's going to be 30 times 4 times 60 times 60 to get the time, so that's 432,000 seconds. And then we're going to use energy equals power times time. We're given the power of 60 watts. 60 times 432,000, so that gives us an energy of 2.59 times 10 to the 7 joules. And for y, energy equals power times time, the time is the same. So 11 watts times 432,000 seconds equals 4.75 times 10 to the 6 joules. So we can see the difference in terms of the energy converted. 2 marks, one for each correct answer there. For part 2, suggests why the two lamps can have different power ratings but have the same light intensity output. So Y transfers less to thermal stores and the same as X to light or luminosity, therefore it transfers less energy per second overall. You can have a converse argument for X, so X transfers more to thermal stores and the same as Y to light, and therefore transfers more energy per second. Okay, so 1 mark for saying Y transfers less to thermal stores, and 1 mark for saying the same as X to light or luminosity. For 3, we've got a battery in a laptop computer which has an EMF of 14.8 volts and can store a maximum charge of 15.5 times 10 to the 3 coulombs. The battery has negligible internal resistance. Calculate the maximum amount of energy the battery can deliver. So we're going to use the equation W equals QV. So the first mark is for using that equation. Multiply the charge by the potential difference, 15.5 times 10 to the 3 multiplied by 14.8 equals 2.26 times 10 to the 5 joules. So 3 significant figures. 1 mark for using the equation, so substituting values in, and the second mark for the correct answer. B, the average power consumption of the laptop is 30 watts. Estimate how long the laptop can be operated from a fully charged battery. Give your answer in hours. So we're going to find time from energy equals power times time. We've just calculated the energy, and we know the power rating now is 30 watts. So 2.26 times 10 to the 5 equals 30 times T. And then we're going to rearrange that and solve it for T. So T equals 2.26 times 10 to the 5 divided by 30, which is 7,548 seconds. And then converting that to hours, it's 2.1 hours. It does say give your answer in hours, so we have to read that very, very carefully. Otherwise we will drop a mark. Question 4. Well, firstly, A part 1, define resistivity. So always go for an equation, but make sure you state what each of the symbols are in the equation. So resistivity rho is equal to RA divided by L, where R is the resistance, A is the cross-sectional area, and L is the length of the material sample. So you've got to have cross-sectional area here, not just area. So we're talking about taking a slice through the material and finding the area of that section, which is called the cross-sectional area. So first mark for the equation, second mark for giving all of the correct terms for each symbol. Part 2, state the significance of the critical temperature of the material. So at this temperature and below, the resistance or resistivity becomes 0, or the material becomes a superconductor. Or you can say the maximum temperature at which resistivity is 0. So there's 2 marks there, one for saying at this temperature and below, second mark, resistivity or resistance becomes 0. For B, given a sample of tin in the form of a cylinder, has a diameter of 1 mm and a length of 4.8 meters and a resistance of 0.70 ohms. use these data to calculate the value of the resistivity of tin. So using that equation, rho equals RA divided by L, the first thing is going to be to calculate the area from pi r squared. So we're going to need to half the diameter and put that into the pi r squared, and that gives us 7.85 times 10 to the minus 7 meters squared. That will be a mark. The second mark is for correctly substituting in the resistance and length values into this equation. So 0.7 and 4.8. That could be a mark on its own if you got the area incorrect. And then the third mark is for the final value, 1.14 times 10 to the minus 7 ohm meters. So written here as 1.1 to 2 sig fig would be correct. And then the fourth mark is for the unit, which is ohm meter. So resistivity has the unit ohm meter. If diameter is used instead of radius, the answer is going to be 4 times the above, and you would lose 1 mark. So you could still get 3 marks out of 4. Question 5, we're calculating resistance of this copper wire, 0.75 meters long, cross-sectional area 1.3 times 10 to the minus 7 meters squared. So we're going to use the same equation, but this time to find R. R equals rho L divided by A, and we are given all of the values. We don't have to do any calculations of area, we're given that. So we're going to substitute the values in. 1.7 times 10 to the minus 7 multiplied by length 0.75 divided by cross-sectional area 1.3 times 10 to the minus 7. That gives us 0.9807 or 0.98 ohms to 2 significant figures. The value should be at least 2 significant figures. You would get the mark if it was more than 2 significant figures were shown. But if it's less than 2 significant figures, you would lose them. You wouldn't get the mark there. Okay, B, part 1. A 12 volt, 25 watt lamp is connected to a power supply of negligible internal resistance using 2 of the connecting wires. The lamp is operating at its rated power. Calculate the current flowing through the lamp. So we've got 25 watts and 12 volts. We can use the power equation. Power equals IV, current times potential difference, rearranged. So current equals power divided by potential difference. 25 divided by 12, which equals 2.083 or 2.1 amps. To 2 sig fig, 2.08 is accepted, perfectly fine. 2 marks there, 1 for substituting in the values into the equation and 1 for the correct answer. B part 2, calculate the potential difference across each of the wires. So this time using V equals I times R. And we know the current, we've just calculated it, and we know the resistance as well, we've calculated that. So this is an example of where we're using previously calculated values. So you can carry the error forward. The mark here is for using the values that you've calculated and multiplying them together. So V equals I times R, current times resistance. 2.08 times 0.98 equals 2.038 or 2.04 volts. Okay, and part 3 calculates the EMF, which is the electromotive force of the power supply. So if internal resistance is 0, which we're told in the question, then the EMF is going to equal the terminal potential difference. There's no lost volts inside the resistance of the battery or the power supply. So therefore the EMF is going to be equal to the sum of the potential differences across the components. So we can simply add those together. So we've got 12 volts plus 2.04 plus 2.04 volts equals 16.08 volts. which equals 16.1 volts. And so we're just using the values that we've got here. We've got a 12 volt lamp, and we've got 2.04 volts across each of the wires that are connecting it. So it's a 12 volts for the lamp, and it's 2.04 volts across each of the connecting leads. So in total it's 16.08 volts, 16.1 volts. Part C. The lamp used in Part B is connected by the same two wires to a power supply of the same EMF, but whose internal resistance is not negligible. State and explain what happens to the brightness of the lamp when compared to the brightness in Part B. So there would basically, the lamp is less bright, so there will be some lost volts now, which reduces the terminal potential difference, and that then reduces the current, and that reduces the brightness of the lamp. So the lost volts is IR in this equation. There's now a potential dropped across the battery, and that reduces the EMF, or that reduces the terminal potential difference. The EMF is the maximum energy the cell can supply. That's reduced by this lost volts amount, IR, to give you a lower terminal potential difference. And that then means that the lamp will decrease in brightness. Or we can say the lamp is less bright because energy is wasted in the resistance of the cell. So just taking a simple kind of energy transfer argument is fine as well to get 2 marks. Question 6. A student investigates how the power dissipated in a variable resistor Y varies as the resistance is altered. Figure 1 shows the circuit the student uses. Y is connected to a battery of EMF, epsilon, and internal resistance R. So we've got the graph here, which is the power against resistance graph. For this circuit, as the resistance of this component variable resistor is changed, we are measuring the power, and we're seeing how it changes. So the first question is A. Describe how the power dissipated in Y varies as its resistance is increased from 0.5 to 6.5. So it increases to a peak at 3 ohms and then decreases steadily down to 6.5. So it increases to a peak at 3 ohms, or you could say 3 watts, that's the power level at 3 ohms, and then falls between 3 and 6.5. That's fine, 2 marks. B part 1, the EMF of the battery is 6.0 volts and the resistance Y is set at 0.80 ohms. Use data from figure 2 to calculate the current through the battery. So from the graph, 0.8 ohms gives 1.9 watts, values between 1.9 and 2.0 accepted. We use power equals I squared R to find the current I, because we've got the resistance and the power. So I squared equals 1.9 divided by 0.8. I equals a square root of that, which equals 1.541, or 1.5 amps. Values between 1.5 and 1.6 are accepted. For B part 2, calculate the voltage across Y using V equals I times R. So we've now got the current and the voltage, so it's 1.5 amps times 0.8 ohms equals 1.2 volts. So it's the current times the resistance. We're given the resistance in the question here, 0.8 ohms, and we've just calculated the current, 1.5 amps. So another example of where we're using a previously calculated value, and this time a value that's given in the question. And this is very often the way questions go. And so you can have an error carried forward here if you've got a different value for the current in B part 1 and used that correctly in B part 2, then you can get both marks here for B part 2. B part 3, calculate the internal resistance of the battery. So we're going to be using this equation, which is V equals E minus I R, which is the equation for the terminal potential difference, the EMF and the lost volts across the cell. So 1.2 equals 6 minus IR. So we're told we've got the 1.2 here, the voltage across the Y, 1.2 volts. We're told that the cell has an EMF of 6 volts at the top in the question, and so we can work out the lost volts. So it's going to be 6 minus 1.2, which is 4.8 volts, and then from that work out R, small r here, is the internal resistance of the cell. So it's going to be 4.8 divided by 1.5 equals 3.2 ohms. So values between 2.9 and 3.2 are accepted, and again error carried forward is fine. So if you've got a different value for the potential difference here but use that correctly, then that's absolutely fine. You can still get the 2 marks. Oh, you've also used a current value there, which you calculated as well. So if that was different, but you've used it correctly again. So that's why there's a range of values accepted, because you can have ECF, error carried forward values. Part C, the student repeats the experiment with a battery of the same EMF but negligible internal resistance. State and explain how you would now expect the power dissipated in Y to vary as the resistance of Y is increased from 0.5 to 6.5 volts. So we've got the EMF is equal to the terminal potential difference now, because there's negligible internal resistance. We'll assume there's none. So the EMF is equal to terminal potential difference, which equals 6 volts, and that's a constant terminal PD. So as R is increased, P would decrease, because we know that power is inversely proportional to resistance. So if power is V squared over R, V is constant, then power is inversely proportional to 1 over R. So if R is increased, then P would decrease. So there's 3 marks here. You can see the red ticks. This mark is available if you've then gone on to say power is inversely proportional to resistance. So this mark, P equals V squared over R, only really makes sense if you then use that to say that the power is inversely proportional to resistance. You could just say that power is inversely proportional to resistance without the V squared over R, and that would be a mark as well. Okay, so check that one to see if you've got all 3 marks. Question 7. So this is the diagram showing a trace on the screen of an oscilloscope. The Y sensitivity is set to 5 volts per division, so that means that each square, which is a division, is equal to 5 volts, and the time base is set to 0.50 milliseconds per division, so that means that each square here is 0.5 milliseconds. So for the trace, determine the maximum positive value of potential difference. So this is the 0 line here. Then we've got 2 divisions at 5 volts per division. So it's simply 2 times 5, which equals 10 volts. That's a mark. Part 2, the maximum negative value of potential difference. So the trace goes just 1 division below the 0 line, negative. So that's going to be -1 division times 5 volts, which equals 5 volts. Should really be -5 there, but it's okay to write 5 volts. And then part 3, the frequency of the signal. So we're going to use time period. We're going to find time period, and then frequency equals 1 over time period. So time period is 3 times 0.5 milliseconds. So each square is 0.5. So one whole trace, or one whole oscillation, if you like, is 1, 2, 3. So this is where it starts to repeat. So 1, 2, 3 divisions multiplied by 0.5 equals 1.5 milliseconds. 1.5 times 10 to the -3 seconds. And then using f equals 1 over t, so 1 over 1.5 times 10 to the -3 equals 667 Hertz. So you can see how the marks are awarded here for this part of the question. B, the trace shows the variation in the potential difference across a 100 ohm resistor. Calculate the energy dissipated in the resistor. So part 1 for the first 1.00 milliseconds. So power equals V squared over R, which is -5 squared over 100, which is 25 over 100, which is 0.25 watts. And then using energy equals power times time for 1 millisecond, so 0.25 times 1 times 10 to the -3 equals 2.5 times 10 to the -4 joules. Can use, instead of V squared over R, you can use I equals V over R, and then P equals IV. Essentially it's the same thing, but just with 2 steps involved. For part 2, between 1 millisecond and 1.5 milliseconds, again same method. Power equals V squared over R, so it's 10 squared divided by 100 ohms equals 1 watt, and it's for half a millisecond, so it's 1 watt times 0.5 times 10 to the -3 seconds equals 0.5 times 10 to the -3 joules, 5 times 10 to the -4 joules in standard form. Only 1 mark for this second part and 2 marks for the first part. And 5 marks in total for B part 1 to B part 4. So, and then just carrying on this question, part 3 in one cycle. So one complete cycle is going to be adding together the 2 energy values that we've got here to give us a complete cycle. 2.5 plus 5 equals 7.5 times 10 to the -4 joules. And then in 1 second, it's going to be 0.5 joules. So the calculation is shown below. So it's 7.5 times 10 to the -4 joules in 1.5 times 10 to the -3 seconds. So to get that as joule per second, we're going to divide 7.5 times 10 to the -4 joules divided by 1.5 times 10 to the -3 seconds gives us 0.5 joules per second, which is the power rating of the resistor. Or you can use 667 Hertz, the frequency, multiplied by the 7.5 times 10 to the -4 joules will give you the same value. So you've got this many cycles and you've got this much energy per cycle. So that's now the end of the electric circuits questions run through. If you have the workbook, you've got the mark scheme here, and you can always have a look through that as well. But hopefully the explanations that I've given have made it a little bit easier for you to see what's needed in each question, rather than just having to try and interpret the mark scheme. So anyway, I hope that was helpful. Thank you very much for watching. Bye for now.